So good morning, a little bit of a warm up using the activity series with our single replacements. See if you can figure out or predict the products of these reactions. See if you can predict the products. Okay, so even if you're not finished, that's okay. Let's just check your progress. Remember, for all of these, we're going to have to check our activity series. And the way this works is that this has to be more reactive or higher on the chart than what it's replacing. And even though on the metals, hydrogen is listed there, hydrogen is a non-metal, but this is one of those times where hydrogen acts like a metal. It's part of the activity series. So we compare the activity of these metals. Are they more or less reactive with hydrogen? So the way we tell is by the position of the metal on the chart. So if we look at the metal on the chart, find hydrogen, and then find copper. You tell me out loud, yes or no, is copper more reactive than hydrogen?
No,
How do you know, Ray?
it's closer to the least reactive, to the bottom of the thing, right?
Because in order for it to be more reactive, copper would have to be higher on the chart, right?
Yes, ma'am.
So if copper is below hydrogen, then copper is less reactive. So
Yes,
you're
ma'am.
right, Ray. You're right. This is be a no reaction. Nothing would happen. Nothing would happen. Looking at number 2, magnesium versus copper. So find them on the periodic table. Compare magnesium versus copper. Now you tell me, is magnesium more or less reactive than copper? Tell me out loud.
It's more.
How do you know?
It is above copper.
Very good. So since it's above copper, then it's going to be more reactive. So will this reaction occur?
Yes.
It sure will. So now we're going to have to write our new species. But we have to check copper or magnesium is +2, sulfur is -2. So do we need any additional subscripts? We're good because a +2 and a -2, they balance each other out. They add up to 0. Now on 3 and 4, it's the same process. It's just that instead of doing metal replacement, we're doing halogen replacement. Remember, halogens are those that are in group 17. So looking at the first one, iodine, who is it going to try to replace? Sodium or bromine? Tell me out loud.
Bromine.
Bromine.
Exactly, because bromine is the other halogen. So we still have to look, and the chart is a lot smaller. Is iodine more or less reactive than bromine?
Less.
So what does that mean, Bobby?
It means it's not gonna react. It's
Right,
no
no
reaction.
reaction. So if this guy is below, he is less reactive, and this does not happen. You're exactly right. Doesn't happen. Last one. Will this reaction happen? Yes or no?
Yes.
It sure will. And so now I'm going to have potassium with chlorine reacting with Br, giving off Br2. Do I need any subscripts on this one? I'm good because my charges end up as 0. A positive one and negative one equals 0, so I don't need any subscripts. How come I wrote BR as a 2? Anybody know why I did that? Tell me out loud. And you can't say because I'm the teacher.
Because the chlorine's going to break into 2, so you need to account for them in the equation
Oh, wait just a minute. How come I wrote BR as a 2?
because you needed 2. Because you needed 2 molecules of the potassium bromide for every one of the chloride 2s.
Not yet, Bobby. We're not balancing yet, but
Oh.
you're onto something. But
Oh,
the
it's
reason,
Magnificent 7.
yeah, it's one of the Magnificent 7. In other words, it's diatomic. It's a diatomic molecule. Let's practice a little bit with double displacements. Let's practice a little bit with double displacements because we went over those real quick at the end. We'll do this one together. So a couple of reminders. This right here is called a physical state abbreviation. That's called a physical state abbreviation. And so S means that something is, of course, solid. L means it's liquid. AQ means it's aqueous. And that's a solid plus water. Okay, it's a solution. And then a G means it's a vapor or a gas. Okay. So I have water in the system, but water's not taking part of the chemical equation. I just took a little bit of this powder and I mixed it with water. I took a little bit of that powder and I mixed it with water. And now I'm putting 2 solutions together. So when I look at this, a good thing to identify are the ions. So here's my metal ion. Here's my other metal. And it's my metals that are going to switch places. Okay. My metals that are going to switch places. So these 2 are going to switch places. So now I'll write silver with sulfide. You might want to get out your periodic table, especially the ones with the ions. I'll send that to you real quick in case you don't have it handy. But the reason you want your ions handy is because you're going to have to look up and see what are the charges on all these species. Where is it? Okay. So in case you can't find your table, check the chat window. I just sent it. There's also in your book, I just saw it. Page 140. Figure 411 is also a table of ions. So if you don't have your chart, you can't open it. Also check page 140 of your textbook. That's also a table of ions. Yes, Isaac. There is an exception. Sometimes metals replace hydrogen. I shouldn't say yes. So somebody just asked me, do metals always replace metals? The answer is yes, except sometimes they replace hydrogen. And I'll give you an example of when they replace hydrogen. But yeah, metals typically change places. And the reason, if you always want to remember a rule, is because metals always form cations. So cations always replace cations. That's a better way to remember it than metals replace metals, because remember, hydrogen can form a cation as well. So cations replace cations. It's an ion exchange, is what we're looking at, an ion exchange. So what would our new species be? We'd have silver with sulfur, and then sodium with nitrogen. Before you start writing little twos everywhere, this is where practicing your nomenclature is going to be helpful. Remember that your nitrogen, it moves as a single unit, or your nitrates moves as your single unit. So see how I kept the nitrate over here? After I write my formula, now I'm going to go back and check and see if I need subscripts. This is where you're going to have to check your table of ions. Somebody tell me out loud, what's the charge of silver as an ion?
+1.
+1, very good. What's the charge of sulfur as an ion? Oops.
-2.
-2, very good. So these two numbers do not equal 0. So that means I'm going to need 2 +1s to balance the -2 charge of sulfur. So again, those of you that like to crisscross, you can think of the 2 as coming down to go to the silver, and the 1 is coming down to go to the sulfur. So you're going to have an Ag2S. Now let's check sodium nitrate. What's the charge of sodium as an ion?
+1.
+1. Looking at your polyatomic chart, what's the charge of nitrate as an ion?
-3.
Not -3,
-1.
-1. So +1 and -1 equals 0. So I don't need any subscripts. This is good. This is good. So now I've checked my subscripts. The last thing I need to check is my solubility rules. Last thing I need to check is my solubility rules. In other words, I need to predict the physical state of these two compounds to see if any of them are a solid or not. So looking at my rules, which rule is going to be most helpful for silver sulfide? Which rule is going to be the one that I'm going to use?
Rule 4.
Nope.
Is it number 6?
Rule 1.
Nope. Well, rule number 1, we'll use it for this one. That's right. Who said rule number 1?
Andrew.
Andrew, thank you, Andrew. So rule number 1, we'll use it for sodium nitrate. So what is the physical state of sodium nitrate? Is it a solid, liquid, aqueous, or gas? Soluble means it will mix with water.
Aqueous.
Yeah, it's aqueous.
For the first part, wouldn't we use rule number 6?
Rule number 6 would be a good choice for this one. Rule number 6, because it says most, and this is just S, so most sulfide salts are only slightly soluble. Slightly soluble means that it will barely mix. It will barely mix. So slightly soluble is the same thing as insoluble. Slightly soluble is the same thing as insoluble. So we're going to put an S right there because that means it would come out of solution. It would come out of solution. By the way, remember when we were learning the indicators of a chemical reaction, we said if you form a precipitate, that indicates a reaction has formed. This right here is your precipitate. So that means if I was to draw a picture, if you had a beaker and you poured into that beaker some silver nitrate and you poured into that beaker some sodium sulfide, what you would have inside of that beaker is a little pile at the bottom of some probably white solid, and that white solid would be silver sulfide. Floating around in here, you would have sodium ions and nitrate ions, along with water, because water's in the system. But you would have a solid at the bottom, and that solid that would collect at the bottom would be silver sulfide. We'll try another one. Type in a number 1 in your chat window when I can go on to the next screen or to the next paper. Good, good. You're keeping up this morning. That's good. All right. So now we'll try this next one. Okay. So here's what I want you to do. Number 1, let's predict the products. Make sure to check the charges. Okay. Make sure that you check the formulas are correct. And then check the solubility chart. So we're going to predict the products. Make sure you check the formula and then check the solubility chart. So try to do this one, at least predict the products. I'll give you a minute to try this one on your own. Just to predict the products. I don't expect you to finish it completely, but try and predict the products. Okay, so let's check your progress. It's okay if you're not finished. I just want to check and see how you're doing so far. So here's my 2 cations. Iron from this formula, this 3 down here came from iron. If I kind of uncrisscross, so I know that this is a +3. And then potassium on its position from the periodic table is a +1. So those are the 2 that are going to switch places. So I'm going to have FeOH, this is still a +3, plus KNO3, and this is still a +1. If I look at my table of ions. Hydroxide is a -1. Nitrate is a -1. So this is going to tell me whether I need subscripts or not. In order to balance this out, I'm going to need 3 hydroxides, each of them at a -1. So I'm going to need 3 of these whole things. So remember, when you have a polyatomic ion, you use grouping symbols around the hydroxide to say that you need 3 of everything on the inside. A +1 and a -1, they balance each other out. In other words, you add them up, they equal 0, so no subscripts are needed. How well did you do on predicting these? If you got them both right, type in a number 1 into the chat window. If you got one of them right, type a number 2 into the chat window. Good, good. So those of you that missed one of them, I'm guessing probably if you missed one of them, your problem was writing the formulas, which is common. Okay, we're still kind of new to it, but practice, 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 practice. Looking at your charts, practice writing nomenclature, your nomenclature activities. That will help also learning how to write formulas. So practice, practice. All right, somebody tell me out loud, what is the physical state? Check your solubility chart. What is the physical state of iron 3 hydroxide? Somebody tell me out loud, what is the physical state of iron 3 hydroxide? What's the physical state on this?
Solid.
What is it?
Solid.
It's a
Number-
solid. Very good. How did you know?
Rule number 5.
Rule number 5 that says most hydroxides are only slightly soluble, except those. And slightly soluble is the same thing as insoluble. By the way, marginally soluble is the same thing as insoluble. So good job. Somebody tell me, what is the physical state of potassium nitrate?
Would it be aqueous?
It sure would. How did you know that?
Rule number 1.
Very good. Rule number 1. Good job. Good job. Believe it or not, we are not done with this chemical reaction. We're not done. The second thing that we have to do is we have to balance it. The second thing we have to do is we have to balance it. And we do that by adding coefficients. That's all we can add, by the way. Add coefficients only. And the reason that we do this is because we must adhere to the law of conservation of mass. Okay. We have to adhere to the law of conservation of mass. And what the law of conservation of mass says is that the amount of matter in the universe, oops, I forgot, the amount of matter in the universe is constant. In other words, matter is not created or destroyed. It's simply recycled. Okay, matter is recycled. So I'll give you an example, a simple example. Here is the formation of water. Okay, here is the formation of water. This is a combination reaction. Okay, this is a combination reaction. This is hydrogen gas, oxygen gas. They react in a nice, great explosion to form water vapor. This is unbalanced. And here's how I know that it's unbalanced. Look at your periodic table. What is the molecular mass of hydrogen? In other words, how much does this hydrogen weigh? Well, when I look for the molecular mass, what I add up is the mass of all the atoms in this formula. So looking at your periodic table, how much does one hydrogen weigh? Tell me out loud.
1.
1. And how many do I have in the formula? 2. So the molecular mass is 2 atomic mass units. Look at oxygen. How much does one oxygen weigh? Round to the nearest whole number.
16.
16. So if I have 2 of them, 32 atomic mass units. Now, how much does water weigh? Well, I've got 2 times 1, and which equals 2, plus 1 oxygen, which is 16. So water weighs 18 AMUs. Okay. So if I divide my reaction kind of like in half, if I think of this as like an equal sign, then if I add up everything that's over here, the 2 plus 32 equals 34. This is unbalanced because I've got 34 atomic mass units on this side, but only 18 atomic mass units on that side. Therefore, I'm not adhering, or in other words, I'm in violation of the law of conservation of mass. In other words, all of this should equal the same mass as all of this. So all the reactants should have the same mass as all of the products. But in this case, I'm unbalanced. Another way that I can see that I'm unbalanced is if I count atoms. How many hydrogens do I have on this side? 2, right? And then I've got 2 oxygen atoms on this side. But if I go to this side of the equation, somewhere I lost an oxygen atom because I've got the 2 hydrogens. So that's balanced. But I have 2 oxygen atoms and only 1 on that side. It's unbalanced. So in order to make sure that I balance my chemical reaction, what I do is I add coefficients only. I add coefficients only so that I'm in compliance with this idea that the amount of matter in the universe is constant. So I'll show you what I mean by adding coefficients. I'm going to rewrite my equation. Whoops, there we go. I'm going to rewrite my simple equation. Uh-oh. That's supposed to be an H. H2O. Doesn't look like H2O. Here we go. I don't like how that looks. Hold on. There we go. That's better. Okay. So coefficients just like in math, these are whole numbers. Sometimes we think of them as integers. And they are multipliers. Okay, they are multipliers and they're placed at the beginning of a formula. Okay. Now, when you go on to higher level chemistry classes, you'll find that sometimes coefficients can be fractions. For our class, for chemistry 1215, our coefficients will always be whole numbers. But it is possible when you go into higher level chemistry courses that you might have fractions as coefficients. But regardless if they are fractions or if they're whole numbers, they're going to act as multipliers. So I'll show you what I mean. When this equation is balanced, I've got a 2 over here and a 2 right here. Okay, now this equation is a balanced chemical equation. Okay, now it's a balanced chemical equation. And so this number 2 right here, that's an example of a coefficient. This 2 that's hanging off there, that's a subscript. Okay. But the 2 in front, that's our coefficient. So what it does is it multiplies everything that I have after. So if I'm counting atoms, I have 2 times 2, that gives me 4 hydrogen atoms. There's an implied coefficient. Hi, Mom. There's an implied coefficient of a number 1 here. Okay. But we don't usually write them. These are implied. Okay. I'm putting one there just for today, but we typically do not write a number 1 out, but know that the number 1 is implied. That gives me 1 times 2, 2 oxygen atoms. Now in front of my water, I have a coefficient of 2. So if I'm counting atoms again, 2 times 2, that gives me 4 hydrogen atoms, and 2 times the implied number 1, that gives me 2 oxygen atoms. Now you can see that I'm balanced because I've got 4 hydrogens, 2 oxygens, and 2 oxygens. If I was to add up their masses, not only would the number of atoms be balanced, but also their masses would be balanced. So now I am adhering to the law of conservation of mass. So in other words, when a chemical reaction occurs, these coefficients are really what they are. They're the proportions. Okay. They're the proportions in which your reactants and your products are part of the chemical reaction. All chemical reactions must be balanced. For our class, all chemical reactions should be balanced. You'll find when you go on to higher chemistry courses, sometimes they don't balance the equations. They should, but sometimes they don't balance them until like the very end. But for our class, we're going to make sure that our chemical reactions are always balanced. Now, how would you say this out loud? You know, if you were reading this, because part of learning chemistry is learning to read your notation. Well, if you were reading this, you would actually say out loud, you know, 2 parts hydrogen gas reacts with 1 part oxygen to yield 2 parts water vapor. So when you read the chemical reaction, you read the coefficients as part of it. So balancing chemical equations, here's the answer why it's important, is because we must adhere to the law of conservation of mass. In case you see that on a quiz. Oops, of mass. That's why we do it, is because matter's not created nor destroyed. You have to account for all of the atoms that are interacting. And so those coefficients, they end up being the proportions of how things actually react. If you do not have those proportions, there's no reaction. Okay, that's an important idea. If the proportions are lacking, then there's no reaction. So for example, if only 1 part hydrogen gas was present, then the reaction won't occur. Okay, so for this balanced chemical reaction, for it to occur, you have to have 2 parts hydrogen. If you only had 1 part hydrogen, then you don't have enough to start the reaction and it won't happen. So it's not enough just to have the elements available. You have to have them available in the right proportions for the chemical reaction to occur. A lot of detail here. Give me a number 1 when I can go on to the next page, or if you have any questions. Okay, looks like y'all are doing good. Excellent. So let's go back to our original equations that we worked with today, and let's practice balancing them. Okay, let's practice balancing. So one of the equations that we worked with today was this single displacement. We had magnesium solid plus copper sulfate. And then we had magnesium sulfate plus copper metal. Okay. So the way it's written, is it balanced or is it unbalanced? Well, we're going to balance by what we call inspection. And that means we're just going to look at them. So I have 1 magnesium on this side, 1 magnesium on that side, 1 copper here, 1 copper there. Now, instead of counting 1 sulfur, 4 oxygens, 4 oxygens, instead of doing that, I'm going to count this as a whole unit. I'm going to say I've got 1 sulfate over here, 1 sulfate over there. And so if you recognize your polyatomics, that can be helpful when you're trying to balance. So I'm going to write on here, treat as a unit. Okay, treat it as a unit when you're balancing by inspection. And guess what, guys? This one is already balanced. It's already balanced. So in other words, we don't need to add any coefficients. It's already balanced. So the proportions that this reacts is a 1 to 1 to yield 1 to 1. So you need 1 part this, 1 part that, and it will give you 1 part this and 1 part that. It turns out that this one is already balanced. Yay, I love those. Already balanced. Let's try this one from earlier. That's an R. It's a funny looking R. Okay. So what I want you to do is I want you to balance it by inspection. So in other words, examine both sides. And you are going to have to add a coefficient. This one isn't already balanced. I'm going to let you balance it for me by adding only coefficients. You cannot change the little subscripts. Okay, can't change those, but you can add coefficients. This one's not too hard. Try it on your own and then I'll catch up with you. Displacement reactions. Okay, so types of double displacement reactions. So just in general, remember that our double displacement reaction is that ion exchange. But there are certain types. There's what we call a precipitate forming. And that's where you have a solid is formed in the products. One, maybe both. Then you have the formation of a gas. Okay, formation of a gas, and the same thing is that the products are going to form a gas. Then you can also have what's called an acid-base neutralization. And the result is always water and a salt. Okay. So acid-base neutralization is a type of double displacement where you form water and a salt. I'm looking at the time, so I'm going to skip formation of a gas today, but I'm going to go over the acid-base neutralization. So acid plus base yields water plus a salt. And these are easy to spot because all you do is you look at the products, and if you get water and a salt, you know that it's an acid-base neutralization. So for example, if I take hydrochloric acid and I mix it with potassium hydroxide, which is a base, and Isaac, this is kind of your question earlier where I was hesitant to say that it's only the metals that change its places. This is an example where hydrogen kind of acts like a metal and that it will trade places with a metal, but that's because they're both cations. Okay, they're both cations. So it's still an ion exchange. So the result here is water. So H plus OH forms H2O plus KCl. Always. So these are easy to spot because you can always see the water and the salt being formed. Moving on here, I'm not going to do any more examples of that one. But moving on, another type of chemical reaction in general is what's called the burning of an organic compound. Okay, the burning of an organic compound. And the general formula for the burning of an organic compound is you'll have some carbon-based organic compound. It will be burned in oxygen, and you usually see a little triangle over the arrow. That means that there's heat. But if you add plus oxygen, that's implied that it's burning. And you always get the same result. You always get carbon dioxide, plus water, plus, heat is given off. Plus heat. And I'll give you an example. Those of you that are in biology, you'll probably recognize this as aerobic respiration. If you take glucose and you burn it in oxygen, the result is carbon dioxide plus water plus energy, which we usually write as ATP. This is unbalanced. This is a 6, this is a 6, and this is a 6. But aerobic respiration is a good example of burning of an organic compound. Another would be like your Bunsen burner in class. If we were meeting on campus, burning just regular methane, you would still get carbon dioxide plus water. The next time that I see you, we're going to cover what are called redox reactions. And we're going to cover section 1 through section 6 in your book. Okay. Next time I see you. We have about 3 minutes left. Do you have any questions for me? All right, I'm going to put up in Blackboard in this week. I'm going to put up some more worksheets with the answer keys. Are those helpful? Tell me yes or no.
Yes.
Okay, I'll put up some worksheets so that you can practice writing chemical equations. If you're struggling writing equations, nomenclature is helpful. Working on your nomenclature is helpful because this is really, they're kind of two halves of the same coin. Once you get used to writing formulas and reading formulas, then writing chemical equations becomes a little bit easier. But practice, practice, practice. Also, go to other websites. You don't need to just need me to tell you where to go on websites. There's apps on your phone. There's websites that you can visit. So get creative. You know? But unless I have any questions, I'm going to stop recording.